Okay, so we're recording now. It'll be a short recording. So what you do is hit alpha window, option 4, put in your limits of integration, and just keep hitting the right key to move on to the next part. And then you could type this in like in with a bunch of parentheses, but maybe easier to do the fraction mode. So you hit alpha y equals, select option 1, 10x squared, then hit the right key to go down. Then cube root, we'll just raise it to the 1/3 power. I mean, if you want to do cube root, you can. Hit math, option 5, that's 3. Actually, I don't know why I didn't pick the cube root. Oh, it was option 4. That's okay. And then type it in x raised to the 3rd power minus 9. Then you do this in terms of x. You got to put dx, hit enter. There you go.
Wow.
Of course, you got to show your work. But that's how you can verify that you've done this right.
Yeah.
So again, alpha window is kind of your best friend there. It's a really, really nice way to help you. Now, if you happen to have a problem that's multiple parts and you have to use the same equation for multiple parts, there's another way you could do this too. I don't know. Let me see if there's usually on the AP curriculum, they tend to do those kind of yeah, kind of that's kind of happening here for you. Yeah, yeah. It's kind of happening here for you. So I'm gonna jump to 20. Um, so what I would do actually is go to y equals. Okay, I'll get out of here. And they give you the x-intercepts and they want that area, right? So if I at the indefinite integral, well, I mean that's not hard, right? That's just, all this junk here. Which I know you can do because we've already talked about how to do that.
Yeah.
Okay, so then you add 1 to the exponent divided by the exponent, right? Right? You just got to do all that work. And then plus c, don't forget about plus c, right? But c won't matter when you do the definite integral after on. But since they ask for an indefinite integral, you got to put plus c at the end. And then, of course, you could simplify afterwards if you need to, right? Negative 2/5 x5 plus 5x4. Actually, you should simplify, make your life easier. 0.4x cubed plus 54x squared minus 54x plus c. Then you're supposed to find the area of the shaded region. So then you're supposed to do this. And the c's cancel, right? They cancel.
Yeah.
If you plug out, plug 1, plug in 3. And you gotta be really careful when you plug it in because a lot of arithmetic that's going on. But this is where and you teach might want to use may want to see that excuse me, may want to see that process. A plugin which I know is a real pain to do. But in the graphic calculator, because I already punched it in, right? Hit off window, option 4. We're going from 1 to 3, right? Now, we hit y equals, our equation stores y1, right? Hit alpha trace y1. 3.2.
Wow.
So yeah, but you do have to plug in 3, plug in 1, and work through the process. Your teacher's looking for that. But at least you know you can check your work. Because if when you're plugging in and you're not getting that, then there's probably a mistake you may have made with the plug-in in part or the antiderivative or somewhere along the way.
Yeah.
I mean, yes, it's very possible you could have made a mistake in punching it over here too. That's very possible. But at least it just gives you more guardrails, right?
Yeah.
And then what's the average value? Average value, do you know the formula for average value? What to do, the
Um,
process?
no.
It's just the integral, but you do 1 over um, b minus a, or
Yeah.
the limits of integration. The funny thing is that that's just gonna be 1 anyway, so it doesn't matter. Um, doesn't matter at all. And yeah, you just, you know, integrate it from 0 to 1. There we go. Great. And the reason why we call it average value, um, like for example, let's look at our curve again, right? So this is kind of the theory that goes into it. Um, oh geez, it's kind of a funny. Let me let's say we want to find average value from 1 to 3, or say from 1 to 2. Actually, let me make up a curve. So is that 2? Is that 1? So is that 6? Is that 10? Okay, so you got a curve like that, right?
Yeah.
Well, how many points are there from 2 to 6? Do we know?
Um, two, three.
Infinite, actually.
Oh,
There's infinite points from 2 to 6. Like you could have 2.1, 2.35, 4.0001, 3.999. Like there's infinite points.
hmm,
But ultimately, there's going to be some y coordinate that's the average of all those. I know the lowest y coordinate's 1. Well, 10's not the highest y coordinate, but this is probably the highest y coordinate here. I'm not sure what that is. But at the right endpoint, the y coordinate's 10. But at some place, there's going to be an average y coordinate. Because an average, when you add up everything, divide by a number of things. Like, for example, um, if like a basketball player has like like Steph, I haven't really followed the Warriors. I know they're not playing great, but like say Steph Curry has like average 30 points per game, right? How do you calculate that? Take all the points he scored each game and divide by number of games, right?
hmm,
So that's take all the y coordinates and divide by number of y coordinates. Or like your teacher wants to get the class average for a test. How's that computed? They use some sort of Schoology or Canvas or some online grading system, or you could do it by hand, I suppose. But you just add up all the test scores and divide by number of tests or number of students.
yeah.
So that's the same thing. So same thing's happening here. There's going to be some sort of average. Maybe the average right here. Now what you could do is you could draw a rectangle. That's the average y coordinate. That's the difference is 4. So 4 times average y coordinate. Um, that's actually going to wind up equaling. This is called the mean value theorem. It's going to wind up equaling the integral from 2 to 6
Hmm.
of our function. Because there's going to be some moment where, if I pick, it's really the average y value, it's going to equal the area between the curve and the x-axis. So this rectangle equals the area between the curve and the x-axis. Well, if I divide by 4, my average y coordinate will be 1/4 times that integral. And
Yeah.
that's where average value comes from. That's why you do 1 over b minus a. That's the theory that goes into it. So that's what you're trying to find, is you're trying to find the average y coordinate. The problem is there's infinite points, but if you think of it in terms of area, yeah, there's going to be some rectangle I could draw in such a fashion where the height of the rectangle crosses the average y coordinate. That area of that rectangle equals the area between the curve and the x-axis. And the area between the curve and the x-axis, that's a definite integral, right? So the area in green, like for any equation for that matter, yeah. So the integral from a to b equals that integral. So,
Yeah.
or that area, sorry. So that kind of tackles how to do 20. I know I skipped around a little bit. We talked about 6. I know you have to get going soon. We'll come back to 7 and 8. I feel it's important we do talk about 13, a little 15, and then we can end there. Excuse me. So do you know how to approach a problem like 13?
What was that?
Do you know how to approach a problem like 13?
U equals t squared plus 3.
It's a little different though, because you're doing the derivative of it, right?
Mm-hmm. Then not really, no.
Okay. And plus, I'll tell you right now, it's impossible to this integral. You just can't do it.
Yeah.
So we're not going to do the integral. Don't worry about it. But let's do this. Let me show you what happens, and then I'll give you the theory. Here's what you do. Because the derivative and integral, they knock each other out, right? That's the answer. What you do is you take the upper limit, you replace t with it, and multiply derivative by the upper limit.
So how did you get 9?
Oh, I did 3x squared.
Oh, okay.
So that's what you do every single time is you replace t with whatever this is. So let me show you one of my notes on this stuff. Maybe calculus AB. Let's see here. Spring semester lecture notes. It's going to be 6-4, I think. Yeah. So you can see like yeah, so see what happens here is you have the integral from 7 to 5x cubed of tangent of some wacky thing, right? And thus you replace the t's with 5x cubed.
Okay.
And then, but then also you multiply by the derivative of 5x cubed, which is 15x squared. It's part of a chain rule situation. Um, and then that's that. That's what you do. Because the reason why we do that is that you're doing the derivative of an integral. They knock each other out. But why exactly am I replacing t here with the upper limit? How come the lower limit doesn't matter? And why am I doing a chain rule? Like why is all this happening? And I think I could explain this in 3 minutes because I know I need to get going. Um, so
And
let me,
for the derivative that you multiply by,
Mhm.
is that the b value on the
Yes,
interval?
100%.
Okay.
Yes, 100% correct. Exactly, yes. So let me explain why this works. Let's say, just go get something very simple. Let's say I got um, t squared plus 1.
Mhm.
And let's say I'm integrating from 2 to x. Okay, well, the antiderivative I know is t cubed over 3, right? Plus t, 2 to x. Okay, we'll plug in x, plug in 2. Easy peasy, right? Not that hard. Okay, now let's add a little wrinkle here. Let me add a derivative to the left of it. And it's going to carry along the whole way, right? Ah. Now, if I take the derivative, what's going to happen? I'm going to have 3x squared over 3 plus 1 minus 0. Because this is just a constant. I mean, if you want to calculate, I think it's 14 thirds.
Yeah.
So you get x squared plus 1. Great. That's back to what we had, right? Do we have t squared plus 1?
Mhm.
So I just did a swap, just replace t with x. It's all good, right?
Okay.
So what if I change this number to like a 4? Did it matter? No, of course not. Who cares? Because if I put a 4 in here, fine, I get 64 over 3 plus 4, but who cares? Because when I do the derivative, it's going to go away anyway. So as long as the lower limit's a constant and the upper limit's in terms of x, you can just do a replacement. Just replace t with x. Now, what if the top was not x? What if it was like x squared? Okay, not a problem. Now, when I replace t with x squared, I got to do x squared cubed, which is x to the 6th power. And that's x squared. So when I take that derivative now, that's 6x5 over 3 plus 2x. Well, that's not quite the same as this, right? But here's the deal. What? Oh, okay, okay. So you have x4 plus 1.
Mhm.
Because remember, you're replacing t with x, but you know, it's t squared. So you're doing x squared squared, right? X squared squares x4. And then times the derivative of x squared is 2x. Guess what? I get 2x5 plus 2x, which is the same thing I got down here.
Okay.
And so now you know the shortcut. And you see
Okay.
why, because I gave you a simple example to look at. But
And
now, good.
you only do this when there's a derivative
Yes,
for the
yes,
integral,
yes,
and the
exactly. Got it.
integral
Yes,
has x on the top and a
yes,
constant on the bottom.
yes. And so,
Okay.
but so these expressions are deliberately written in a really messed up way that you cannot do the antiderivative. It's impossible. Like you cannot do the antiderivative. It just can't. A use of wouldn't work. Like I don't know. I mean, there might
Yeah.
be some other techniques maybe I just forgot from my old calculus, like advanced calculus classes from back in the day. Like see, same thing here. Now I know what to do. I'm going to replace t with 3x4, square it, that's 9x8, multiply it by 2, that's 6x4. That's the square root. Times the derivative of that, which is 12x cubed. And there you go. That's it. That's all I do.
Okay.
So I think we took care of a very important concept. That's an example of fundamental theorem of calculus. So I think that's good. We did talk about use, so I think we'll need to talk more about that. Do a little more practice. I think would be good. We obviously need to pick things up from where we left off, 7 and 8. We talked about average value, what that means. I think there's some trig stuff that's going to be a little bit tricky that we'll have to handle that. We talked about Riemann sums. We talked about how to deal with the tables, um, area between the curve and x-axis. So I definitely think we'll close all these loops by tomorrow. So,
Cool.
and tomorrow's around the same time still works for you?
Yeah. Yeah. Definitely.
Perfect. Sounds good. Yeah. So I'll see you then.
All right. See you then. Thank you
Bye.
so much.
No problem. Have a good day.
Have a great day. Bye bye.